I think everybody who's looked up at the night sky as a kid and asked very naive questions. What is the universe? What is it made of? How did it begin? And really my question is, how did it begin? I work on what we call the theory of inflation. This is a theory of the very, very young universe, so very close to the Big Bang, about 1 billion, billion, billionth of a second after the Big Bang. So what was going on then? Well, we believe lots of important things happened in this very, very early time. One of which is the universe looks the same in every direction. And obviously, if I look around this room, I see different things in different places. But if I take a big telescope and look really far away, if I look up, down to the north, south hemisphere, I see the same thing over very, very large distances. And nobody knew how this was possible. You may think, well, the universe has reached what we would call thermal equilibrium. There was only a limited amount of time for the young universe, because it hadn't been there for a long time, to send information to thermalize. And so even assuming it thermalized as quickly as possible, it turns out that's way too slow. We should see a completely different universe in the north hemisphere and the south hemisphere, and we don't. We have really only one solution. It's a solution from about 30 years ago, but then it was pure speculation. And this theory is called inflation, or a paradigm. Inflation basically is the very rapid expansion of space. And why does that help? Well, if you think, remember, thermalization takes time. It's limited by the speed of light. So what you want is you have time for a little piece of space to thermalize, just a very small space. Now, if that would not be enough in the normal theory from the Big Bang until today, but now I let a little piece of space thermalize, so it looks all the same, and then I blow it up as quickly as possible. That's what inflation does. And you've made a huge space look all the same. Now, the objection, which many people may think, how can space expand quickly? And in fact, it expands much more quickly than the speed of light. That sounds ridiculous, but it's not. Okay, so if you imagine I shine a light onto a wall. In my hand, I'm holding a laser, which you can see the beam on the wall not very far away from me. And if I move the laser slowly backwards and forwards, you see that laser beam moving slowly backwards and forwards. But now, if I take a step back and do the same thing, you'll see the laser beam is moving more quickly, even though I'm moving my hand at the same rate. And if I could keep stepping back further and further away, imagine I was pointing at the moon, and there was a little green man watching my laser. He would see that moving faster than the speed of light, meaning he would barely see it at all. And it's the same when space expands. Different parts in space move away from each other much faster than the speed of light, but they can't talk to each other anymore. Nonetheless, they've all been given the same initial condition. They've all been told, we are at the same temperature, we all look the same. And once they look the same, they're sent away from each other, they keep looking the same. So that's how you can go from a microscopic piece of space into something actually big, say the size of a football, in like a trillionth of a second. It's just, the miracle is done. They've agreed to all be the same temperature, then they run away at superluminal speeds, but they keep that. They have the memory, and the universe is homogeneous. So in this space which is thermalized, there are nonetheless these tiny quantum fluctuations. They're sort of shimmering away there. And when you blow up space, these tiny fluctuations, which are about 10 parts in a million, so very, very small, their wavelength is blown up along with the expansion. And so what you're doing is you're encoding some memory from inflation onto the sky, which later, these tiny perturbations, believe it or not, they become galaxies. The satellite called the Planck satellite, it went up, and it was measuring what we call the cosmic microwave background. Now, this cosmic microwave background is basically a memory of the Big Bang. It's the leftover radiation. It's been cooled down from incredibly hot to about 3 degrees Kelvin, so minus 270 degrees Celsius. But importantly, it's still there. We can still measure, and we can measure slight differences in temperature. How big are these differences? Well, if it's 2.7 here, it's 2.7000001 in a different direction. And that's telling you about the quantum theory active during inflation, because you've got this snapshot, you've measured, the primordial properties. What's exciting is that different models of inflation, by which I mean slightly different inflaton particles, which is a hypothetical particle, will create a slightly different pattern of perturbations on the CMB sky. And the Planck satellite has measured these perturbations very well. So we can invert the problem and say, given the sky today, 14 billion years later, what does this tell us about the theory of the inflaton particle about a billionth of a second after the Big Bang? When I was applying for jobs, I looked at Sussex as being a very broad place, a place in which I could study the beginning of the universe, along other experts here, but where there are also experts studying galaxies. So we can sort of span the whole history of the universe from this billionth of a second up to 14 billion years later in one corridor here in the University of Sussex.